All right, hello everyone. I'm Carlos, I work at GitHub, and today we're going to go on a tour of a few edge cases and unusual situations that happen when you provide Git hosting to the world at large. So just in case, a bit about GitHub. We're the largest Git repository in the world with over 67 million projects and 30 million users right now. And with these numbers, you can be sure that we see our share of situations that we didn't expect when we initially wrote a bunch of these services. So I work in the Git Infrastructure Team. We're the ones providing the Git service, both to internal and external users. So that's the website, the API, any GitHub pages and internal customers, and also any external customers, such as any of you that runs Git clone. Or even if you run Subversion Checkout, we also are in charge of that one. We're also the ones handling the support escalation for any technical issues or questions about Git performance or .conf performance, that kind of thing. That all gets back to us, and then we also provide input on technical aspects in support replies. So given how popular the website is, we run into a fair share of unexpected use cases and people having ideas about what service we're actually trying to provide. Sometimes it's just not obvious at first glance that something is actually going to cause an issue because, like I said, people make assumptions about how a service operates, and sometimes that's not quite correct. Now, I'm going to name a few repositories in this talk. There's the ones that are public. So I don't necessarily want to harp too much on them specifically. These are some of the ones we have to intervene on, and definitely not the only ones that are behaving in unexpected ways. And most of them aren't even doing anything particularly that we call inappropriate. It's just that we didn't expect them when we originally built some of these services. And sometimes the solution to some of these issues is just social or educational, right? Where we just have to tell the user, okay, well, this is how Git actually works, or this is how we build GitHub with these assumptions in mind, and you're breaking them. So let's figure out a way not to do that. So let's start with our own repository, GitHub. We deploy to about 600 machines on each deploy, and we deploy maybe 100 times a day on a typical day. And this is something we're very proud of. This is something we've spoken about publicly quite a bit, and we definitely want to keep enabling the dynamism that such a deploy rate allows us. But as our machine count increases, that puts more load on the servers that are hosting the GitHub. And now we're using Kubernetes, so the number is faster, but it hasn't become any smaller. So this kind of issue where everyone tries to fetch at the same time, this is what you call a thundering head issue in systems. So let's see, well, all of the machines start at the last deploy, and they all want to update to the new commit. So they all need the same objects. Here is where Git, due to several technical reasons, can't guarantee that it's always going to produce the same data for the same requests. So by default, you can really cache responses. But we had to build our own little tool that sits in the middle called Lariat, because it deals with hertz. And when we detect multiple identical requests coming in, like the second or third one will actually detect that it's concurrent. We can then cache that response in a way that we know that we can actually replay that one. So this allows us to only create 2 or 3 times this pack file, and then we're able to cache it and then send it out from disk instead of having to ask Git every single time for one. And this allows us to actually perform the deploy fairly quickly, and the servers aren't overloaded anymore. And this is something that we also give the customers in the on-prem version, so that because this is also very typical in an internal tool. Someone somewhere in a big organization also tries to deploy all constantly. We see it with AWS. Our customers also see them with their clients. So this is something that we're happy that we can provide to anyone, even if they're running GitHub on their own machines. So the second example is the Kubernetes, K8, Kube, however you pronounce it. This is a project that makes very extensive use of pull requests, and which is good, right? We like pull requests. But every time that you update the base branch, any tab where you have the pull request page open, it will notice this, and then it will ask the server, hey, can I paint the merge button green now? And that, from every tab, from every person that's opening it. And that's a lot of requests. And that requires that we do a test merge and a test rebase. And it's not easy to coordinate all of this because they all have completely different jobs with no notion that any other job is actually happening. So this isn't so much of an issue. Most PRs are small, so the actual merging process isn't that bad. But because we run a distributed system, we need to reach consensus on reference updates. This is where we use a 3-phase commit because it's proven it works, but it's a bit slow. So this is the system we call Spokes, and as part of that, we are limited to maybe a couple of reference updates a second. When you update the base branch and all of the tabs ask at the same time, that can be a few hundred, and that's when it starts going wrong, because we didn't build it with enough slack, unfortunately, to actually deal with this. So the bottleneck becomes actually creating the reference update. So this is the refs pool namespace that you might have seen that CI uses. This is something that we're still sort of working on. So part of the issue, part of the solution is already there, right? So that's grouping whenever possible. But also the client knows that it's okay to retry. This is something where we're also building more smarts into the code so that we can avoid denying any updates to real users and to be able to detect when it's a robot doing the update. And then we can tell the robot, okay, try again later. It didn't work out this time. Because the robot doesn't care, and it's probably some tab that someone opened an hour ago, and they've completely forgotten about it. Anyway, so the human isn't even looking at it. So just the robots don't care about them. And then if you don't care about robots, the scalability issues become a lot simpler, usually. So from some that are sort of more of our issue with the increasing scalability of or scale of our customers, here's something a bit interesting. So a user wrote to us, and usually these are people who are too conscientious to actually have any particular effect on our service. They're usually not much of an issue. But in this case, they were asking if it was okay to have a GitHub raffle in their hackathon. So they wanted to have the 300 people or so that were going to their hackathon to push to a particular repository all at the same time. And then the winner of the raffle would be the person who pushed last before a particular timestamp. Now, they asked us if it was okay for them to do this. We told them no for multiple reasons, one of which just being that Git timestamps are completely fakeable, so they won't even know who won it. And we don't have the capacity to deal with 300 pushes simultaneously. We told them, they did it anyway. I think they changed a tiny little detail about what was going on there, but yeah, they just went ahead with it. And we saw this, right? So this is what that looks like. The red bar you can barely see at the bottom, that's the usual alert level, and this went way beyond that. So they tried to do 7,000 pushes in an hour. They failed, obviously. I mean, even if we didn't have our 3-phase commit system, there's no way we would work. So that's, at least, far from this being just a weird situation, this allows us to at least know that, hey, this actually failed in exactly the way we predicted, and no one else was affected, right? Because all of this request rate and update rate, this hangs off of a particular repository. So no one else, not even any fork from that repository, would have been affected by them not being able to commit because they're basically abusing the system. So this gave us a lot of confidence that the system we had built, we knew how it behaves. Next up, I think I deleted this name. This is a repository with a bunch of, it's called whosonfirst-data-venue-us. So this is about, this is New York data. It's not too big for a repository holding data. And they actually even use multiple nested directories so that it actually performs well, so that all of the trees and all of the objects internally are kind of small. So it's not too heavy maintenance, but that's almost a million almost a million files in each commit. And that adds up because the way we do updates via the web UI is the same way that Git does it. What it does locally is reads in all of the files into the index, updates one, and then writes it all back out. Now, locally, it works mostly fine just because you keep that file around. This is not something we can actually do on the server side because we have thousands of users that are acting on everything. So after a while, we're looking, okay, and figure out what the difference was. Now here, turns out, yeah, this is just on us. So we made the code a bit smarter, right? So we read only the affected paths. These were about 6 files in and 2 directories at the root. So like, why are we also reading everything else? Well, that's how Git does it, basically. So we built a bunch of code that is smarter than just plain local Git. And this made everything better for everyone. So that was a really great case to run into because it just made us, it let us make it better for everyone who updates via the API. So this is both the UI, which that uses the same API to update things, and also any changes via our api.github.com. And the code is in the libgit2 library, which we're using to create this tree, so anyone can actually use this code if they have a similar need on their system. Right, next up we have one which is actually a bit big, about 365 gigabytes. I found it as one of the largest repositories in one of our partitions. So I went in to investigate. Like, well, what could they possibly be doing that requires almost 400 gigabytes? And as far as I can tell, turns out 9gag, this website where people put images they think are funny, they used to have a feed, and then they changed it to an app that showed you ads. So people got angry about this and built their own feeds without ads. Now, one of them was this, but this wasn't just the feed, this was also all of the pictures and videos. So this user was up pushing 300 to 400 megabytes every 10 minutes, every time they updated the RSS feed. Now, they were force pushing, so the reachable size for the repository, whenever you cloned it, this was about half a gig. But because we've built GitHub with the assumption that you actually care about the data that you're pushing to us more than 10 minutes, so we want links to objects, PRs, all that kind of stuff to continue working. So we don't actually delete objects. This is how we get to 365 gigabytes of repository. In this case, the solution is just to tell the user, please don't do that, because it's just not useful to anybody. So yeah, that was. They stopped, which is good, right? I think they're still using us to host the RSS feed, but using EC2 or something to actually host the images. So it's nice when the user says, okay, yeah, I was doing something silly and I'm going to stop. The next one you might have seen in the news, as it were. This is CocoaPods specs. So CocoaPods is a package manager for Objective-C and Swift. And this repository is where it stores its specs, right? That's where it stores the manifest, what packages there are, what the versions are, how to find them. So they have a lot of them, and they update them quite often. So there's about 260,000 commits, which is about half of the GitHub repository, and we've been working on it every day for the last 9 years. So it's a lot. It's a multi-year software, except they reached it in just like 1 year or something. And they have across all about 175,000 files. Now, similarly to, or rather, I mentioned before with the New York data, they actually have multiple subdirectories that are sort of hashing just like you would in a file system, so it performs well. In this case, they didn't. They had a single directory, or a tree as Git has it, with every single package that they had. So these were like several thousand. So every time anybody updates any of the packages, Git needs to rewrite anything leading up to that tree, which means the base tree with all of the different projects. It also has to update it, which is huge for tree standards. It's huge files and huge objects that Git needs to repack whenever we do maintenance. It needs to inflate them, check for compare against other big trees, and see if there's any differences so that I can actually compress the data. This was failing maintenance constantly, and the rate of commits is about 1,000 commits a week. Mostly from robots, as far as I can tell. It just meant that they were constantly failing maintenance. However, how it really came to our attention properly was that every CocoaPods user, whenever they run an update, so that they can update their local list of what versions of what packages there are, they fetch from GitHub. Now, this is every single user whenever they run an update command. And programmers love to have the things, the registry at least up to date. So this happened quite a bit. And we have a monitoring system that actually intercepts and says, okay, well, this repository has been fetching constantly for the last week, so I'm just going to stop it. Well, not completely stop it. What we do is delay fetches or a bunch of other commands until the quota reaches a certain level. So the users of CocoaPods complain to them, saying, hey, this takes forever, and sometimes it just times out. So then they come to us and say, hey, our users are unhappy. And that's when we go in to investigate. So there's a couple of posts in this issue from engineers in our team explaining how CocoaPods had managed to almost make every decision to make it harder for us to host. So they had these huge trees, users constantly fetching from it. And also, they had decided to do shallow clones. So this is where you do git clone -- depth 1, for example. Initially, this can actually help to reduce how much you download. However, due to the way they were merging the pull requests and to do with the graph, they ended up always fetching all of the history anyway. But because they had done this depth option in the beginning, that meant that our Lariat caching layer wasn't able to cache, because whenever you have all of this shallow clone, a lot more computation has to happen server side. So now not only could we not use the caching, the actual fetch that was happening was more expensive than it would have been otherwise. And to boot, they weren't actually saving any space in their clients' machines. So yeah, this was a fun one. So we asked them to do the fetches more efficiently and to use smaller and nested directories, right? This is just called sharding. This is what you do for a file system as well, right? A file system with a directory with thousands of entries doesn't perform well. Git doesn't either, because it's basically a representation of a file system. So I think it took a while for everything to get in line, because then people had to update their clients and then undo the depth thing. But I mean, it's gone all right. However, one of the other things we did, because that would still been pretty expensive, we also spread the load around all machines. So we have this distributed system. So we have 3 to 6 replicas of each repository. And we generally read from just a single one so that we can make use of the caching in each machine, so that the file system is cached in RAM, and then everything can be a bit faster. But that means that the quotas are also applied on per machine, which means if all of the CocoaPods users are going to the same machine, they fetch from the same machine, right? And all of the quotas are being applied to everyone from the same machine. So we spread it out. Currently, they're on 6 different machines that we read from. Which means that we almost never actually apply any quotas. So I mean, we definitely decided not to ban them or anything, because it was, well, it's a big useful project. So we definitely wanted them to and their users to be able to keep using their CocoaPods packages. This is where I start cheating a little bit and add halves for honorable mentions. This is for it's a couple of things that have happened, or repositories that we've discovered since I last wrote out the talk. So this Hubble is a security compliance stack. It contains configuration. This repository in particular contains configuration for this. However, they had set up their client, similar to CocoaPods, to test every minute, whether to try to update every minute, right? Test whether there's any updates across all clients. So they had 13.7 million fetches in a day. That's 3% of all fetches across all of GitHub. So we were not amused. However, the monitoring layer caught this, so we were able to actually so we were able to avoid the servers being actually overloaded. So they had similar issues where their clients would just stall because the way we enforce this quota is, like I said, we stop operations from happening for a while until the quota is back to an acceptable level, and then we don't throw it anymore because then we want the clients to have the data as fast as they can and then go away. So we kept throwing for a while, and then contacted the owners of the project and said, hey, what are you doing? Can you maybe fetch less often? So they changed it to think twice a day, and they're also looking at moving to something that's actually a CDN rather than us, which is sort of accidentally a CDN for anybody who wants to push data to us. We also did, like with CocoaPods, move the reading to all 6 replicas. So now we barely enforce the quotas, and this is what that looks like. You can hopefully tell without the arrow when we spread the load around to the 6 replicas. So everyone's happy for a while. Hopefully we don't have to do this again for them. So here's this next one's a bit of an interesting case because no one's really trying to do anything unusual. It's actually very, very helpful, right? So this is barryclark jekyll now. This is a repository that you can fork, and then you have your own GitHub Pages site that's set up with Jekyll, a lot more than if you just create a new repo locally. So the issue here, or well, one issue here is that each fork is someone's website, which means that they all have different contents. And we've built GitHub, and Git itself is built in the with the assumption that when you fork, that's going to be the same project. So most things are going to be the same. Most files are going to have the same content. And then someone's going to do a small change, and then maybe with a pull request or not, but it's going to be all very similar. This is quite the opposite. From the point that they fork, everything's completely different. This means that it's more expensive to store. It's more expensive to perform a clone for each of these repositories. But it's not too bad. I mean, it's fine as long as you clone every once in a while. Whenever someone updates, we clone it through our GitHub Pages workers and then render it. However, we found that there were a group of servers that attempted to clone all of them at the same time. Because we serve forks all from the same machine for the caching reasons I mentioned earlier, it got a bit busy, right? So this is our 32-core machine with a load average of 400. That was because of the particular way they had done all this cloning, they had actually managed to bypass the quotas a little bit. And because we were already past the applying quotas, we let all of them run wild and try and get try to get done with the clones as quick as possible. Now in this case, there were so many that we could barely do any progress. And here, well, we saw this was like a small group of IPs in the same data center, so we figure, maybe this is not actually a user that's really interested in all of these people's blogs. So we just banned the IP addresses, and everything went well immediately. Like, oh, okay. So yeah, we've actually been playing around with expanding the scope of the quotas from the monitoring. But this is something that happens very, very rarely, and it has knock-on effects on other networks where really there are actually multiple very active forks, like Linux kernel, for example. So we just figured, well, sometimes you just have to ban a few IPs and move on. So that's what we did. This next one was an interesting interaction. So we had this repository that we're pushing multiple times a minute, which is fine. We can deal with that on the reference update side. However, that means that we were accumulating small chunks of changes, so we want to run maintenance on this so that we can package everything up together. Right? This is the same thing that Git does when you fetch a lot, then after a few commands, Git will say, oh, hey, there's too many objects here. I'm going to run a garbage collection run. We do kind of the same on the server, just a lot more controlled. We have a lot more data. Now, this meant, so this repository, because they were constantly pushing, like all the time, for days straight, it meant that by the time we finished maintenance, there were already too many incremental updates, so that we had to run maintenance all over again. And to make it worse, one of the replicas fell behind, and that one could never catch up, because by the time we managed to sync everything over to the new machine again, we had already accumulated so much data that they could just never keep up. So we, and especially with the name, hey, CI logs, okay, what are you doing here? So we emailed the owner of the repository, asking them, hey, what are you doing? And like, maybe could you not? They come back and say, well, yeah, we tried this experiment like 6 days ago. We turned it off. I'm like, are you sure about that? Can you double check? And they're like, yeah, sure enough. This was like an academic IP range, so we figured it was some grad student that had not been careful enough when they thought they shut down their experiment. Yeah, so once they actually double checked, turns out they had a process pushing to GitHub. It's also empty commits, which is also extra weird. And then that process was, for some reason, spawning other processes, which were also pushing, and also spawning other processes. So at one point, it just reached like hundreds of processes all trying to push at the same time to GitHub, all a bunch of empty commits. I don't know, academic experiments, I guess. Not sure there's a big lesson to get out of this. Just make sure you turn off your things. And speaking of commit rates from academic projects, this tool is from a university group as well, I believe in Canada. We found they were pushing about 4 commits a minute. It's not a problematic rate, but you have to wonder what they're actually doing. Right, so I discovered this. I was looking through backup logs, and I said, okay, turns out every hour when trying to run some garbage collection, there's like over 200 incremental updates from this, right, which means 200 commits from this particular repository. What on earth are they doing? So I go looking like, okay, this is like a weird content, and they had actually accumulated 110,000 commits, which is multiple years of an actual software development. And yeah, this is one of those cases where you try locally to use Git as a database, and it works great because you have 5 things, and then you try and use it in production, and it breaks down. Unfortunately, this time it broke down on our servers instead of theirs, so they had no idea that this was actually causing people to have to run maintenance manually and actually distract them from actually trying to make the system better instead of trying to deal with this. So as far as I can tell, they were actually trying to do a workflow queue, essentially a job queue, and this was all the metadata. So instead of using a database, they're like, hey, GitHub's kind of like a free database for us. So we emailed them and hey, it's cool if you want to do this, but like not on our servers, and please stop recommending on the README for the tool that you use it on GitHub, because that's not going to go well. So they said, okay, fine, sorry, and then they stopped, which is good. And I think hopefully they're now using an actual database with database semantics instead of trying to to push Git into being a database, right? This is sort of the same issue that happens with CocoaPods and something else we'll see later on. So this was fine. We said, okay, you're doing something silly, and they stopped, so that's fine. So here I have a standing for a bunch of like any large network. So for example, Torvalds Linux is about 1 gigabyte to clone, roughly. It has 18,000 forks. As you might guess, we don't use 18 terabytes on it, because we just ran out of disk space if we did it for every popular network. So say network, I mean repository network. This is whenever you fork, all of these forks are called the repository network, and then what we do there is deduplicate the actual contents of the data. So this is using 55 gigabytes. The reason it's not just over one is that the people do have forks and actually have. So there are companies that instead of having their own thing, they fork from Torvalds Linux and actually apply their changes on this to their fork of the Linux kernel. So which is how it's supposed to work, right? But this means that, yeah, we're using about 55 gigabytes to store multiple copies of the 1 gigabyte. Now, yeah, some of this is just internal bookkeeping that we're also trying to improve. We keep like lists of all of the references from all forks, which we'll see now in IntelliJ how that's a bit of an issue. So IntelliJ is about 3 gigabytes, 1.8 thousand forks, but it's about the same size. Now the project itself is bigger, but it's not enough to make up for the difference. Now the interesting thing about IntelliJ is that they really love tags. They tag everything. So the main fork, that is JetBrains IntelliJ community, that one has 52,000 tags. And now when you fork a repo, we copy out all of the tags. Whether that's a good idea is a different discussion, but that's what we do. Which means that for the 1.8 thousand forks, we're doing bookkeeping for 1.8 thousand times 52,000 tags. So we have a master list of all of the references. Here, that's about 7 gigabytes out of the 55 gigabyte size. Now, Git being Git, in order to fork, Git needs to read this file into memory multiple times, which meant that earlier this year, it actually became impossible to fork IntelliJ, and so we applied a small optimization. And this is something we're still working on because it's still way too big and maintenance is still way too expensive on this repository. And something to really show how, I mean, it's still more efficient, but it's still not as efficient as we'd like, how this bookkeeping that we do on the whole forking thing. So the Octocat spoon knife, that's, if you've done a training with us, you might know about it. It's the one we use to teach forking, pull requests. So this one has 93,000 forks. This is also an issue on the website. I think it shows just 5,000 plus pull requests because it's too expensive to just even count them in the database. And yeah, so you can see this is a 160K file. I think it's a single file or two, right? 160K. If you clone it, we're spending 9 gigabytes of it for it in its own, just for the network. And not tags or anything. This is just, well, we have a lot of forks, which means we have a lot of different changes, little changes people have made. All of the pull requests have extra bookkeeping costs. And here is just something you always have to be on the lookout for small optimizations, because when you run at the scale of, oh, this file is 7 gigabytes, maybe let's rate it a little less, that immediately helps a lot. So my last example here is an interesting one. It brings up this sort of weird use cases and things you definitely didn't envision. This one where we have 345,000 files overall, or in each commit, I mean, right? 150,000 commits in a few weeks, and 26,000 individual authors in that repository. So this is weird, right? Because like 26,000 people for a small, say small, a lot of files, but it's not a big, it's not something like IntelliJ where, you have a lot of, or the kernel where you have a lot of people contributing to it, right? This is an unknown thing. So it turns out this is a repository for a companion app to a programming learning website. And they were using the repository for their users to write about what they learned. So this is like a blogging thing, like it's a tiny thing, right? But what they were trying to do is commit in each user's name so that it would actually appear on their contribution graph, right? That's the different shades of green boxes that we show in the profile. And their idea was like, well, if they blog with their app and then they push it up to our servers, then we will count them as their contribution, and then that means that they'll actually get a green square and they'll stay committed, right? So the commit here, as far as I can tell, refers to being committed to learning. Now, putting everything in the same place has some of the similar situations that I mentioned before, where maintenance is really, really expensive. And this also meant that we had, the contributions were also very expensive because there were a lot of contributions in the same repository, constantly updating. Again, they had 26,000 contributors, so they had 26,000 entries in a particular directory that we have to keep updating. So all of the things we've already seen before. And here, like, okay, maybe you want to teach people about programming, you want them to commit, but this is really not the way to do it. Like, please don't do this. We're happy to host their blog or whatever if they want to have it, right? Like, I mean, their app can even create the repository for them and commit on their behalf. They just need to authorize it, right? But this is so beyond what we expect people to do. This is not something that and there's a better way, right? So this is not something this is not a use case that we're going to be supporting here. They also got to write a blog post about how they broke GitHub, which, I mean, fair enough, they broke their bit of GitHub. I mean, thankfully we're set up so that it didn't actually affect the other repositories. So just a bit of a conclusion at the end. What do we take from all of this, right? Well, first off, when you're running this kind of service for everyone, your users are going to surprise you, and that's okay, right? Part of the job is to learn from what your users are trying to do with your service, right? They come in, they learn about what you do, and then they try and push the edges. And that's okay, and the job is to learn from that and try to make it work, as long as it's within reason. Some of these use cases were just not a natural extension to what GitHub, the collaboration side, does. And sometimes, just reach out to the user, ask them, what are you doing? Why are you doing this? And, a few places, okay, we'll work with you to make it so that it actually behaves the way that GitHub actually behaves, so that you actually make use of GitHub in a proper way, and we're not, having to wake up 3 a.m. to fix your repository. And yeah, there's always something new, and you're going to be learning a lot if you just let people give you data and just push to you. Thank you. From me.
Custom fixes for them.
Right.
Is that scalable, or is that introducing technical debt into your infrastructure? Are you then having to maintain that custom fix just for that repo, or does it apply to all repos and everyone benefits?
Should I repeat the question for the video? Okay, so it's about the custom fixes, whether that adds technical debt to us. Some of them do. Some of them are quick fixes. A lot of this stuff, however, is working with upstream Git. And slowly we're trying to fix up the patches, make them prettier for upstream so that we can actually send them. For example, I think for the process that creates the pack files for when you clone, there's a few performance improvements we have that we're slowly sending back upstream. There's the thing with the New York data that make it more efficient to create new trees out of old ones. That stuff that's upstream now in libgit 2, and you can do it. If you have that need, you can use the library to do that kind of thing. Sometimes it's just how we run things. So like the whole network thing, it's just how we do things. So it's not adding anything. It's not adding any diversions from upstream, because it's just what we do. And I think so. and because we have this 7 gigabyte file, and Google also has these issues, we're working with them to have a new database format essentially for the references, so that we can be a lot more efficient server side. And there's also some patches that will apply even to the current system for everyone. Like the original idea was to mmap, so to directly read the files from disk, where we store all these references. That never actually happens. So what Git does is read it all into memory and then parse it. So we're creating, well, someone else in my team is creating patches to actually run mmap on that file, so that we can actually read straight from disk and only the bits that we actually need. And that should be making it upstream at some point soon, hopefully, after we've tested it out on our machines.
In the example you gave about 9Gag,
Yeah.
was the repository size due to the repository storing large binary content?
Yeah, so the question is about the 9Gag repo where it's 365 gigabytes, whether that's about the binary size. Yeah, so that was because of all of this user was pushing to us all of the files, all of the images and all of the videos. So those add up. And because we don't actually delete them when you first push and overwrite the history, as it were, it just keeps accumulating. And that's how it gets to 300. I mean, I discovered, I think last night, another 100-odd gigabyte repo with a name like backup something something. So like, it's private, so I can't look into what's actually inside. But we emailed the user asking, hey, what's up? Yeah, again.
And related to my previous question was, so I mean, I know that Git historically doesn't really support large binaries. So were such repositories a reason why Git LFS came about?
Yeah, so the question's about these large files and whether that's why Git LFS exists. Yes. One of the things we keep hearing about when we show up to like games conferences is like, developers are like, yeah, we love Git, but like we have gigabytes of just designs that the like models, pictures, that's things you have in a game, so it looks pretty. So and that's basically how it came about. Say, okay, well now we're gonna have a tiny file and then push it up, and then the real file actually exists somewhere else. That's one of the main reasons for Git LFS is the need to have large files in some trees that you don't necessarily want to put into Git. Well, if there's no more questions, then I'll take my leave.